for number 12, I'm going to zoom in just a little bit. It says if Vmax is equal to 150 micromolar per minute and the initial velocity is equal to 75 micromolar per minute at this substrate concentration for an enzyme that obeys Michaelis-Menten kinetics, what is the initial velocity of the reaction catalyzed by the enzyme if the substrate concentration is equal to 37.5 micromolar? Okay, so I'm going to write down what we're given, because if I write it down, I think you'll be able to see just how or just why we're able to solve it the way that we do. And this is a very good question, so make sure that you're paying attention to these values. So we're told that Vmax is equal to 150 micromolar per minute, and we're told that the initial velocity is equal to 75 micromolar per minute at this substrate concentration. So at a substrate concentration equal to 75 micromolar. So if we draw a Michaelis-Menten graph, and you don't have to do this, I'm just showing you because it's good to give you an example, that's why. So this is your Michaelis-Menten graph, and this is the curve. Now, what is the name of this upper limit right here? That is called Vmax. All right, so Vmax for this problem is equal to 150 micromolar per minute. So here's what I want you to see. They told us that with this substrate concentration, we were able to achieve 75 micromolar per minute as our initial velocity. So what that means is that at that substrate concentration, our initial velocity is 75 micromolar per minute, which, and here's what you should be paying attention to, which is exactly 1/2 of the Vmax. So at this substrate concentration, we have essentially achieved 1/2 of the Vmax. So this right here is about half. So this point right there, this is 1/2 of your Vmax, and it was achieved using this much substrate. And what is that amount of substrate? It is 75 micromolar. So what this means is that this is our Km, because remember, Km is equal to the substrate concentration at which your initial velocity is 1/2 of the Vmax. So if you're ever given a problem like this, they may not give you Km, and you'll have to see from the velocity that you're given and the maximal velocity, you'll have to see that whatever substrate concentration they may have given you, that might actually be your Km, which you'll need to solve the question. So that's what we have here. 75 micromolar is equal to Km. All right, so now that we know Km, we can use our Michaelis-Menten equation for a Michaelis-Menten enzyme. So initial velocity is equal to Vmax times the substrate concentration over Km plus the substrate concentration. So we know Km, we know Vmax, and we know the substrate concentration that we're working with, which is 37.5. That's exactly what they told us at the end of the question, or what I told you at the end of the question, because I made it up. All right, so initial velocity is equal to 150 micromolar per minute times 37.5 micromolar over 75 micromolar plus 37.5 micromolar. All right, make sure that you always write out the units whenever you're doing any of these calculations. A lot of people don't like to write the units, but if you write them down, then you're most likely to end up with an answer that has the correct units. And sometimes your professors might try to trick you. They might. Professors are usually really nice, and the last thing that they want to do is play with you on an exam. Okay, so if I multiply this, I get 150 times 37.5 divided by 75 plus 37.5. What that gives you is 50 micromolar per minute. These are your units. So the correct answer is A. Whoa. There you go. The correct answer is A. Alright, so I hope that that question made sense, or I hope that the solution made sense. Alright, so let's move on to number 13. So it says that we have 5 micromole of a Michaelis Menten enzyme in a buffered solution at a pH of 7.4. That's irrelevant. Kinetic analysis of the enzyme resulted in the following rate constants. So these are our rate constants. What is the Vmax? And assume that the enzyme has only one active site. So a lot of people might think that since we're given a bunch of these rate constants, that we can easily find the Km, which is true. You can find the Km this way. But that's actually not the way that we should go about this question. And the reason for that is because we can use the Michaelis-Menten equation for velocity. And you'll see that even though we do have Km, we don't know the substrate concentration, and we don't know the Vmax, which is actually what we're looking for. So we can't use this equation. And we also don't know the initial velocity. So we can't use this whole thing. But there is another thing, or another equation that we could use. And that is this one. Vmax is equal to Kcat times the enzyme concentration times the number of active sites. So N is the number of active sites. And for those of you who don't know what an active site is the part of the enzyme that actually catalyzes the reaction. So let's pretend none of this was here. I'm going to re-explain it. So there's no need to go back. Whoa. There we go. Me and technology, we don't mix. Okay. So the active site of the enzyme is pretty much the part of the enzyme that actually catalyzes a reaction. And the active site is made up of two things, the binding site and the catalytic site. So the binding site is essentially the arm of the enzyme which grabs the molecule and holds it in place, and the catalytic site is the other arm of the enzyme which catalyzes a reaction, which changes the substrate into a product. So something that's very important for you to know about the binding site is that it is complementary. It's complementary to the substrate. So what that means is that it's complementary to the substrate, to the molecule, so that it can actually attract the molecule. So let's pretend that this blue region right here, the blue region on this enzyme, is a non-polar region. If this region is non-polar, then that means that the molecule that it's attracting must also be non-polar, because these two things attract each other. So therefore, we can say that the structure of the enzyme, or of the substrate, it's made up of non-polar regions as well. So we can pretend that this molecule right here is a drug, and that this enzyme is responsible for metabolizing that drug, and the reason why that enzyme is even able to bind to this is because of this complementary region, which is a non-polar region. The binding site could also be polar, or it could be ionic, but it just has to be complementary to the substrate. Remember, The whole point of the enzyme is to grab a substrate to catalyze a reaction. And how does it grab that substrate? It must have a complementary binding site to that substrate. So by complementary, it must be nonpolar if the molecule is also nonpolar, and it must also be the correct shape for that molecule. So this is very important for you to conceptualize. It's going to come up in the next few chapters. Okay, so N is the number of active sites, and for this one, we can assume that the enzyme only has one active site. So therefore, N is equal to 1 for this problem. And we know the amount of enzyme that we have, which is 5 micromole, but we're not given a volume. So whenever they don't give you a volume, just assume that the container has a volume of 1 liter, and that means that the enzyme concentration is 5 micromolar. All right, so we know the enzyme concentration, and we also know Kcat. Kcat is equal to K2. Cat just means catalytic rate, and that's the rate at which the enzyme is able to turn substrates into products. So here that rate is 5.3 times 10 to the second. So Kcat is equal to 5.3 times 10 to the second per second. That means that it's able to turn 530 substrates into products every 1 second. So this is 530 reactions per second. And you can visualize this as enzyme plus substrate forming enzyme substrate complex, and then enzyme plus product. So this right here is your K2 or your Kcat. So that means that we're going from here to here 530 times per second. So we're forming 530 products per second. All right, so now we can just go ahead and plug these into our equation. This is our equation right here. So we can plug all of these values into this equation. So Vmax is equal to 5 micromolar times 5.3 times 10 to the second inverse seconds times 1. So Vmax is equal to, what is that? 26.5 micromolar. No. 26.5 times 10 to the second micromolar per second. And so we have to convert this to millimolar. So to do that, we do 10 to the 6th micromolar is equal to 1 molar. And 1 molar is equal to 10 to the 3rd millimolar. And if we do that, we get 2.65 millimolar, and that is our final answer. So the answer is B. All right, so now we're going to talk about inhibition kinetics, which is everybody's favorite subject. And more specifically, we're going to talk about the reversible inhibitors. So reversible inhibitors only. Okay, so here we have a Michaelis-Menten graph on the left-hand side. And if we were to connect all of these dots, we would get a graph that looks just like this. Okay, anytime that you're given a Michaelis-Menten graph, the first thing that I want you to do is I want you to find your Vmax. So if we do that together, we'll find that this right here, this upper limit, is our Vmax. So that is our maximal velocity. Here's a conceptual question for you. can you raise the Vmax by adding more substrate? So if you were to add more substrate, could you raise the Vmax? And the answer is no. If you want to increase the Vmax, right here, you have to add more substrate, or you have to add more active sites, which you can't do. That's the number of active sites that an enzyme has is it's a fixed number. Yeah, you could always invent a new enzyme, but nobody has time for that. Okay, so back to this. Whenever you're given a Michaelis-Menten graph, the first thing that I want you to do is I want you to find your Vmax. Because once you find your Vmax, then you can find your half of the Vmax. So what's half of 0.2? That would be 0.1. So half of the Vmax belongs to this point right here. So that means that this right here, this is the amount of substrate necessary to achieve 1/2 of the Vmax. And so that is going to be our Km value. So whenever you're looking at a Michaelis-Menten graph, find your Vmax, find half of the Vmax, and whatever amount of substrate was necessary to achieve 1/2 of the Vmax, that right there is your Km value. And if we scroll down, we can see that this second point right here corresponds with that velocity of 0.1. So 0.066, that is our Km value. So the reason why I want you to find your Vmax and then your half of the Vmax is because that gives you the Km value. All right, so that's what you got to do for Michaelis-Menten graphs, and the equation that gives you a Michaelis-Menten graph is this one right here. Initial velocity is equal to Vmax times the substrate concentration over Km plus the substrate concentration. So let's say that we wanted to take the inverse of this equation. What we would have to do is raise everything to the -1 power. And what that does is you take the inverse of both sides. Okay, so pretty much all I did was I took both sides of the equation and I flipped it. Now we can break down this equation just a little bit further until we get 1 over initial velocity is equal to Km over Vmax times the substrate concentration plus substrate concentration over Vmax times substrate concentration. So all I did was I broke up the Km and the substrate concentration that were on the numerator. And so now I'm going to cancel out this right here, and I'm going to rewrite it as 1 over initial velocity is equal to Km over Vmax times 1 over substrate concentration plus 1 over Vmax. And if you see what we have, we now have the equation of a line in the form of y is equal to mx plus b, where 1 over initial velocity is your y, Km over Vmax is your slope, x, which is your independent variable, is equal to 1 over substrate concentration, and your y-intercept is equal to 1 over Vmax. The reason why we do this, the reason why we take the inverse of the Michaelis-Menten velocity equation is so that we can get a Lineweaver equation. The Lineweaver equation. Lineweaver-Burk. No hyphen. Lineweaver-Burk equation. And so what this essentially means is that if we take the inverse of all of these x values right here, And if we take the inverse of all of these y values right here, we will get these values over here. Which will give us this, this line of slope Km over Vmax. So the slope is Km over Vmax. This right here is your y-intercept. And this point right here, this one specifically, this is your -1 over Km. So this point is very important, and I want you to look for it every time that you're given a Lineweaver-Burk plot. So whenever you're given a Lineweaver-Burk plot, the first thing you should look at is your -1 over Km, which is your x-intercept. And then the next thing you should look at is your 1 over Vmax, which is your y-intercept. So your y-intercept is 1 over Vmax, and your Km is, or your x-intercept is -1 over Km. So those are two things that you should be looking for whenever you look at a Lineweaver-Burk plot. Just like whenever you look at a Michaelis-Menten graph, you're looking for Vmax, then you're looking for half the Vmax so that you can find your Km value. Okay, so we still haven't even begun talking about inhibitors just yet, but looking at Lineweaver-Burk plots and looking for your -1 over Km and your 1 over Vmax, that's a very important skill for you to know for this upcoming exam. All right, so what I did here is I took the exact same graph that I had above and I added an inhibitor. So this line right here represents the Michaelis-Menten graph without any inhibitor. So this is inhibitor concentration equal to 0. We'll say 0 millimolar. And then this one right here, this line, represents the same reaction with an inhibitor concentration of 0.035 millimolar. So essentially what we've done is we had a reaction going on, enzyme plus substrate forming enzyme substrate complex, and then enzyme plus product. We had this reaction going on, and then all of a sudden we introduced an inhibitor which would slow down this reaction. Okay, so then we find our 1 over Vmax, like we always do whenever we're given a Michaelis-Menten graph. We find our Vmax, yes. And then you find your 1/2 of the Vmax. That's this point right here. And that is going to be our Km value. Now, whenever you have an inhibitor, you have to look for the apparent Km. So this Km right here, the one that goes all the way up to this point right here on the blue line, on the blue graph, this is your true Km. This is what the Km is of the enzyme when there's no inhibitor present. But if we look at this orange graph, the orange dots on this graph, what is the substrate concentration that was necessary for us to achieve 1/2 of the Vmax? So here's the Vmax, and then we find half of the Vmax, and I'm going to do it in green. So I'm going to go from half of the Vmax to the line, and this point right here, this substrate concentration is roughly, this is your apparent Km. So essentially what happened is we had a reaction, enzyme plus substrate forming enzyme substrate complex and then enzyme plus product. But once we introduced that inhibitor, look at what happened to the Km. It used to be this number right here, and it shifted all the way over here to whatever this number is. I know that it's at 0.2, but I don't think it's exactly 0.2 on the data. So essentially what we have is a shift in Km, and because the Km has been shifted, this is now called the apparent Km, because the Km is apparently this number in the presence of the inhibitor. Alright, so that's what you gotta do for Michaelis-Menten graphs. Look for the Vmax, look for half the Vmax, and then interpolate to the graph to find your Km, and then to find your true Km, or your apparent Km. Alright, same thing with Lineweaver-Burk plots. The first thing you do is you look for your -1 over Km. So this is your true -1 over Km, and under the presence of an inhibitor, look at what happened to the -1 over Km. It shifted to the right. So if the Km shifted to the right, that means that the Km actually increased. Because if Km increases, then the reciprocal of that decreases, which would make sense because it's closer to the point of origin, to 0. So the Km shifted to the right. What can we say about the Vmax? So this right here is 1 over Vmax without any inhibitor, and this right here is the 1 over Vmax with the inhibitor. It's roughly the same point, so we can just say that it didn't change whatsoever. Okay. So this right here is the substrate concentration. This right here is the velocity without any inhibitor, hence why it's called experiment 1. And then experiment 2, we throw in the inhibitor, and then these are the velocities that we get. And then to get all of these values, you just take the reciprocal. Alright, so now that we know what inhibitors do, which is they slow down reactions and they affect Km, now we can start talking about different types of inhibitors. So the first type of inhibitor is the competitive inhibitor, and the competitive inhibitor has a mode of binding as follows. The competitive inhibitor competes for the same active site as the substrate, and as a result, the competitive inhibitor binds at the free enzyme. So this is your competitive inhibitor, and it binds with the free enzyme, forming the enzyme inhibitor complex. So because the inhibitor is binding here with the free enzyme, what do you think is happening to the amount of free enzyme in solution? Is it going up or is it going down? So because the inhibitor is binding to the enzyme, forming the enzyme inhibitor complex, the amount of enzyme is decreasing. So in order to counteract this change, the equilibrium shifts to the left according to the Chatelier's principle. So because the amount of free enzyme is decreasing, the equilibrium shifts to the left, and this means that ES is unbinding and becoming free enzyme and free substrate. So what does this mean in terms of Km? This means that the Km is increasing, and an increased Km means a decreased affinity of the enzyme for its substrate. So Km is increasing, and that means a lower affinity of enzyme for substrate. So whenever the Km increases, the enzyme has just lowered its affinity for its substrate. So it doesn't really want to bind to it anymore, and that's what we see here when it starts unbinding. Okay, so Km goes up. Now what about Vmax? So because the inhibitor is competing for the same active site as the substrate, we can draw this little enzyme right here. So this is our enzyme, and this right here is the natural substrate, and this right here is the inhibitor. So if you see here, they both have this little round part, which is what binds to the enzyme. So they're both competing for this active site right here. But if we were to increase the amount of substrate, we could lower the chances of the inhibitor binding and only allow substrate to bind. And check this out. Once the substrate has bound, we form the enzyme substrate complex. And then once we form this, we can form enzyme plus product. So we're able to form the same amount of products, and therefore Vmax stays the same. So I'll say it another way. Vmax doesn't change because we can outcompete the inhibitor. Yeah, I think that's good. So Km increases and Vmax stays the same. Even though the velocity is decreased in the beginning, as long as we add more and more substrate, we can outcompete the inhibitor and essentially not let it bind to the enzyme so that it won't form, which will not allow it to form the enzyme inhibitor complex. If we are able to increase the amount of substrate, this will allow Vmax to stay the same. All right, so what does this mean? If the inhibitor and the substrate are both competing for the same active site, this means that the inhibitor and the substrate must look similar, at least in some respect. So I'll make a note right here. The inhibitor must resemble the substrate. All right, so before we move on, let's draw the Lineweaver-Burk plot. So this right here is a Lineweaver-Burk plot, and the x-axis is 1 over substrate concentration, and your y-axis is 1 over initial velocity. If we have this reaction running without any inhibitor whatsoever, this is what the line will look like. But as soon as we introduce a competitive inhibitor, this is our 1 over Km, our negative 1 over Km. As soon as we introduce the inhibitor, the competitive inhibitor, the Km increases. So that means that this line is going to shift to the right. So this right here is going to be our negative 1 over Km, the apparent value. So the Km is going to shift to the right because Km is increasing, so the inverse decreases. And Vmax stays the same, so it's going to have the same y-intercept. And remember, this is 1 over Vmax. So the line is going to look a little something like that. So if you ever see a Lineweaver-Burk plot that looks just like this, where Vmax stayed the same and the only thing that shifted was the x-intercept, you know that you have a competitive inhibitor. All right, so let's go for an example. So in both Dr. Marsh's and Dr. Taylor's class, you will see the competitive inhibitor Viagra. And so what Viagra is, it's an inhibitor of the enzyme cGMP phosphodiesterase. So phosphodiesterase, we can call this PDE. So Viagra is an inhibitor of cyclic GMP phosphodiesterase. And the reason why it's an inhibitor of this enzyme is because it resembles the natural substrate. So this right here is the part that it resembles. If you look at this part of cyclic GMP and this part of Viagra, notice how they look somewhat the same. So what this means is that because these are the regions that look the same, this is where the enzyme must bind. This is where the substrate and binding site lands on the enzyme. Okay. So here's a little bit of backstory. Cyclic GMP is made out of guanosine triphosphate, which is a nucleotide that is in the cells of your body. And guanosine triphosphate binds to an enzyme called guanylyl cyclase. And guanylyl cyclase cleaves this part of this substrate, cleaves this part right here, and it binds this oxygen with this phosphate. It's going to bind this oxygen with this phosphate. And if you look at cyclic GMP, this is the oxygen, and that's the phosphate that are now bound. So this is the bond between them. So that's how cyclic GMP is made. So guanylyl cyclase takes these two phosphates, cuts them off, and then connects this oxygen to this phosphate, giving you cyclic, this is the cyclic part, cyclic GMP. And this right here is regular GMP. Notice how this oxygen and this phosphate are not connected. All right, so cyclic GMP phosphodiesterase is inhibited by Viagra because they both look the same. Even though these parts right here don't necessarily look the same, that's what you need for a competitive inhibitor. Some part of the substrate must look like the natural substrate. Some part of the inhibitor must look like the natural substrate. Okay, uncompetitive inhibition. The mode of binding is as follows. For the regular reaction, you have enzyme plus substrate forming enzyme-substrate complex, and then this forming enzyme plus product. Uncompetitive inhibition, the inhibitor only binds to the enzyme-substrate complex. So that's the inhibitor, and it binds to the enzyme-substrate complex, forming the enzyme-substrate inhibitor complex. And as the inhibitor is binding to the ES complex, what is happening to the concentration of that? Is it increasing or decreasing? It's actually decreasing. And because it's decreasing, the equilibrium will shift to the right to counteract that change. So the concentration of ES is going down, so the equilibrium shifts to the right to increase the concentration of ES. So there's more binding occurring, and what this means is that the Km is decreasing. All right, now because the inhibitor is binding to the enzyme-substrate complex, what this means is that it's forming the enzyme-substrate inhibitor complex, and this does not allow for the formation of product. So it's like the enzyme has the substrate and it's about to catalyze the reaction, but the inhibitor binds and it blocks it from forming any product whatsoever. And so what the Lineweaver-Burk plot looks like is this. So your x-axis is 1 over substrate concentration, your y-axis is 1 over velocity. This line right here represents the normal reaction without any uncompetitive inhibitor. And the Km is decreasing, so therefore, because the Km is decreasing, it's going to shift to the right. The line shifts to the right, and Vmax is also decreasing because we're not able to form any product. We're not able to outcompete the inhibitor. With competitive inhibition, you could outcompete it, but with uncompetitive inhibition, there is no way to outcompete it. And the reason for that is because once you form that ES complex, that's when the inhibitor binds. And so you're not able to compete with it because the substrate has already bound to the enzyme. So the line is going to shift to the right, Vmax goes down because we're not forming any products. So if Vmax goes down, the reciprocal increases, which means that this line is going to shift up, where the x-intercept shifts up. And so then that is what our line is going to look like. All right, and so the inhibitor binds at an allosteric site. So binds at an allosteric site. And what an allosteric site is any part of the enzyme that is not the active site. And it only binds once the substrate has already bound. All right, non-competitive inhibition, classic, pure. So the inhibitor mode of binding for a non-competitive, classic, or pure inhibitor is as follows. Enzyme plus substrate forms enzyme-substrate complex, and then you get enzyme plus product. So with a non-competitive, pure inhibitor, you're going to get the inhibitor binding to both the free enzyme and the enzyme-substrate complex. So the inhibitor binds here. Here you form the enzyme inhibitor complex. Here you form the enzyme substrate inhibitor complex. And because it's a pure non-competitive inhibitor, it's going to bind to both of these equally well. And because it binds to both of them equally well, there's going to be no shift in equilibrium. So therefore, Km stays the same. I'm going to try to be a little consistent tonight. Km stays the same. So what can you tell me about the Vmax? If we're forming the enzyme substrate inhibitor complex, are we able to form any product? Yes or no? No. Because we're forming the ESI complex, we cannot form any product. So that means that because we formed this complex, we also cannot outcompete it, because the inhibitor will bind at this complex, the ES complex, and knock out ES so that it doesn't form any product. So because we're forming ESI, the Vmax also goes down. All right, here's a little spoiler alert for all the other enzymes, for all the other inhibitors. Vmax will always go down, with the exception of competitive inhibitors, right? Vmax stays the same. All the other Vmaxes are going to go down. If Vmax ever increased, it wouldn't be an inhibitor whatsoever. It would be an activator. So don't ever think that Vmax increases. It doesn't increase. Not if you have an inhibitor. Otherwise, it would be a horrible inhibitor. Okay. So this right here is the Lineweaver-Burk plot for a non-competitive classic pure inhibitor. This line right here represents what the reaction looks like without any inhibitor present. And once we add an inhibitor, the Km stays the same. So therefore, it's going to cross the x-axis at the same point. And the Vmax goes down. So if Vmax goes down, the reciprocal 1 over Vmax increases. So that'll be over here. This right here is your 1 over Vmax. And this right here is your apparent, this point right here. That's your apparent 1 over Vmax. So the line is going to look like that. So if you ever see a Lineweaver-Burk plot that has the same x-intercept as the reaction without any inhibitor, that means that Km stayed the same, and so you most likely have a non-competitive pure inhibitor. And this one also binds at an allosteric site. Okay. All right, before we go on to non-competitive mixed, let's just establish one thing. Km is equal to the substrate concentration at which your initial velocity is 1/2 the Vmax. Never forget that. But Km is also a measure of affinity. So Km is the affinity of the enzyme for its substrate. All right, Km, it's the affinity of the enzyme for its substrate. So it's a property that belongs to the enzyme. Okay, so if Km increases, affinity has gone down, affinity down, and if Km decreases, then this means that affinity has gone up. So now the enzyme wants to bind more to its substrate. Affinity up. Ki is just like Km. Ki is the inhibitor concentration at which the enzyme, at which the velocity has achieved 1/2 of the maximal inhibition velocity. So Ki is equal to the affinity of the enzyme. So it's a property of the enzyme again for its inhibitor. Km is equal to the substrate concentration at which half of the enzymes are bound to substrate, which is 1/2 of the Vmax, and Ki is equal to the inhibitor concentration at which half of the enzymes are bound to the inhibitor. Those two definitions, they may not be as important to you right now, but it's good for you to keep them in the back of your mind. So the reason why I say half of the enzymes is because if you have half of the enzymes, so let's say Vmax is equal to K2 times the amount of enzymes times the number of active sites. If you have half of the enzymes, so if you have 1/2 of the enzymes, then essentially what you have is 1/2 of the Vmax, which is consistent with what Km and Ki are. They're the substrate and inhibitor concentrations at which you've reached 1/2 of the either maximal inhibition or the maximal velocity. All right, so Ki is the affinity of the enzyme for its inhibitor, affinity of the free enzyme. So the free enzyme being this free enzyme right here, not this one. Ki prime is the affinity of the enzyme substrate complex for its inhibitor. These right here are all very important for you to know. So with non-competitive classic pure, what you have is an inhibitor with Ki equal to Ki prime. This is really important for you to know. For non-competitive classic pure, Ki is equal to Ki prime, and that's because the enzyme binds to the inhibitor. The free enzyme binds to the inhibitor at the same rate as the enzyme substrate complex binds to the inhibitor, right? Because the inhibitor binds to both equally well. With non-competitive mixed, you're going to have, with non-competitive mixed, you'll have the normal reaction, but here's the difference. with non-competitive mixed, you're going to have the same reaction where the inhibitor binds to both the free enzyme and the enzyme substrate complex, but not equally well. And I'll show you exactly what I mean. Oof, I messed that one up. All right, so with non-competitive mixed, you're going to have the inhibitor still binding to both the free enzyme and the enzyme substrate complex, but look at the top one. Notice how it binds better, hence the large reversible arrows. The inhibitor binds better to the free enzyme on this one, but here the inhibitor binds better to the enzyme substrate complex than to the free enzyme. So with non-competitive mixed, it's the inhibitor either binds better to the free enzyme or it binds better to the enzyme substrate complex. So if it binds better to the enzyme substrate complex, then this means that the equilibrium will shift, or if it binds better to the free enzyme, then the equilibrium will shift to the left. And if it binds better to the enzyme substrate complex, then it'll shift to the right. So that's the main difference with the non-competitive mixed. It's going to bind better to the free enzyme or to the enzyme substrate complex, but it's still going to bind to both. Hence why you have these highlighted regions. Okay, so then for this one right here, where Ki is less than Ki prime, what Ki less than Ki prime means is that the enzyme has a higher affinity for the free enzyme has a higher affinity for the inhibitor than the enzyme substrate complex has an affinity for the inhibitor. Right? Because Ki prime is the affinity of the ES complex for its inhibitor, and a smaller Ki means greater affinity. So Ki, if Ki is low, so a small Ki equals high affinity, and a large Ki equals low affinity. So just like how large Km means low affinity and how a small Km equals high affinity, the same is true for Ki, and the same is true for Ki prime. Alright, so if the equilibrium shifts in the direction of the free enzyme, then what's going to happen is Km is going to what? Is it going to increase or is it going to decrease? Think about it for a second. If the ES complex is degrading and it's going back to enzyme plus substrate, so does that mean that it's unbinding or that it's binding more substrate? That means that it's unbinding more substrate, so that means that the affinity has gone down, which means that the Km has increased. So Km is increased, and look over here, the inhibitor is still binding the enzyme substrate complex, forming ESI, which, as you recall, means less product is being formed, which means Vmax is going down. And over here to this one where Ki is greater than Ki prime, if Ki is greater than Ki prime, that means that the enzyme is more likely to bind, or the enzyme substrate complex is more likely to bind the inhibitor than the free enzyme, which is what you see over here. So if it's more likely to bind, if the enzyme substrate complex is more likely to bind the inhibitor, that means that Km has gone down. I misspoke. So if the equilibrium shifts to the right, that means that the Km has gone down because there's more binding of enzyme to substrate forming the enzyme substrate complex. So that's why Km has gone down. And because we are forming this enzyme substrate inhibitor complex, Vmax has decreased. Yeah, it's decreased. Jeez, I gotta stop making so many tiny little mistakes. Don't worry, everything here is correct and factual, and it's something that your professor would be proud of. So don't worry. All right, so this right here is what the Lineweaver-Burk plot will look like when there is no inhibitor present. And if we were to introduce a non-competitive inhibitor with a Ki less than Ki prime, then what this means is that Km has increased. So if Km has increased, the inverse has decreased. So this is where the x-intercept is going to shift to the right, because the x-intercept is -1/Km, and if Km increases in the presence of an inhibitor, the reciprocal -1/Km has just decreased. And Vmax goes down, so if Vmax goes down, that means that the inverse has gone up. So this is what the graph will look like. And this is what the graph will look like for a non-competitive inhibitor where Ki prime is less than Ki. This line right here represents the reaction without any inhibitor whatsoever. And if we introduce a non-competitive inhibitor that has a Ki prime less than Ki, that means that the enzyme substrate complex is binding to the inhibitor, which means that the Km is going down, which means that the reciprocal -1/Km is going to increase, which means that it's going to shift to the right, to the left. Okay, and so Vmax is going down, so therefore the reciprocal is going to increase, and it'll increase like that. So this is what the graph will look like then. Okay, so that's what a non-competitive inhibitor mixed is for Ki being less than Ki prime and for Ki prime less than Ki. Yeah. And they all bind at an allosteric site. Okay, so for your exam, you should be able to look at all of these Lineweaver-Burk plots and say, hey, I know what type of inhibitor that is. So before we move on, can you tell me what type of inhibitor is displayed on this graph? You have all the tools in your toolbox. You have all the tools in your toolbox to be able to tell me right here, right now. So this line right here represents the reaction enzyme plus substrate forming enzyme substrate complex and enzyme plus product with no inhibitor present. And this line right here is with the inhibitor present. So look at the Vmax. The 1/Vmax is about the same. So 1/Vmax true is approximately equal to 1/Vmax apparent. Remember, the apparent value is the value in the presence of the inhibitor. And this right here is our -1/Km. The line has shifted to the right, which means that Km has increased. So we know Km has gone up, which means lower affinity. So what inhibitor do you know where Vmax is the same, but Km has increased? Good job. Competitive inhibitor. Excellent work. You make me proud. Competitive inhibitor. So that's the type of inhibitor that we have in this Lineweaver-Burk plot and in this Michaelis-Menten graph. Notice how Vmax stayed the same, roughly the same, but look at Km. Km used to be this value right here, but then Km became this value right there. And remember, Km or competitive inhibitors, they must look like the natural substrate, at least in some respect. And over here with cyclic GMP and Viagra, this highlighted part is the part, or this highlighted part right here is the part that looks just like cyclic GMP, and that's how the enzyme is able to bind to the inhibitor at the active site. All right, so let's do some problems now. Number 14. I gotta stop saying so many times. I'll work on that. Okay, so an inhibitor binds to an enzyme that has a true Km of 1.0 times 10 to the negative 6 for its substrate and an apparent Km of 1.0 times 10 to the negative 6 molar. Look at this. The Km values, the true Km and the apparent Km are the exact same. So what type of inhibitor do we have? Excellent work. You make me so proud. Because the Km didn't change, that means that we have a non-competitive. Is it mixed or pure? We have a non-competitive pure inhibitor. Because non-competitive pure inhibitors are the ones where Km stays the same. So here's non-competitive mixed, Km changes, and non-competitive pure or classic, Km stays the same. None of the others do that. Okay, so because of that, we have a non-competitive pure inhibitor, and we know the Vmax, it is 1.0 times 10 to the negative 4th molar per minute, and they want us to calculate the apparent Vmax in the presence of this much inhibitor, and this is the Ki. And remember, Ki is the affinity of the free enzyme for its inhibitor. And for a non-competitive inhibitor, what can you tell me about Ki and Ki prime? Ki is approximately equal to Ki prime. You can say they're the same. So if we know Ki, then we also know Ki prime. All right, so because we know we've got a competitive or non-competitive pure inhibitor, that means that we're going to use this equation over here. The equation for apparent Km is just the Km, the regular Km, and the equation for apparent Vmax is this one over here. So let's write it out. The apparent Vmax is equal to the true Vmax over parentheses 1 plus the inhibitor concentration over Ki. So this is the equation for apparent Vmax. So let's see what we have. We have the true Vmax, which is this value right here. And we know the amount of inhibitor, and we know the Ki. So we've got everything that we need to be able to solve this problem. So the apparent Vmax is equal to the true Vmax, which is 1.0 times 10 to the negative 4th molar per minute. Always write your units. Trust me, one day you'll thank me. Over 1 plus the inhibitor concentration, which is 1.0 times 10 to the negative 3rd molar, over 1.5 times 10 to the negative 6th molar. So So let's punch this into our calculator. I probably shouldn't say punch it into your calculator. That's a little violent. And we got 666, which is a great number. Plus 1, that's 667.66. .66. And so the answer is the apparent Vmax is 1.5 times 10 to the 7th, to the -7th molar per minute. Always write your units. And so the correct answer is D. All right, let's move on. Number 15. What type of inhibitor does the following graph best describe? So this right here, remember, every time you're looking at a Lineweaver-Burk plot, I want you to go straight to the -1/Km. So this is -1/Km right there, and this is 1/Vmax. What has happened to the Km as the inhibitor concentration has started to increase? That's what this arrow means, that the inhibitor concentration is increasing. So what has happened to the Km and the Vmax? Since the 1/Vmax has increased, that means that the Vmax has gone down. And look at this, the Km, or the -1/Km, has shifted to the left. So has Km decreased or has it increased? Because it's shifting to the left, which means that it's becoming larger, that means that the Km is becoming smaller. Okay? So Km has gone down. I hope you'll forgive when I misspeak a little. But yeah, essentially it's going to the left, which means that Km has gone down because it's getting larger, and this is what you need to know. So what type of inhibitor do you have? You have a Km goes down, Vmax goes down. You have an uncompetitive inhibitor. Uncompetitive inhibitor. Okay. And let's prove that. Km went down and Vmax went down. Uncompetitive inhibitor. Boom. That's it. Good job. Okay, number 16. What type of inhibitor does the following graph best describe? First thing we got to do is look at our -1/Km. What has happened to the Km? Excellent work. It has stayed the same. Km is the same. What about our Vmax? Since it's increasing on the y-intercept, that means that the Vmax has gone down. So what type of inhibitor do you know where the Km stays the same but the Vmax goes down? Perfect. That's exactly it. Non-competitive inhibitor. Man, you're on fire. Good job. One day I'm going to be just like you. That's a real compliment. All right, so we have a non-competitive inhibitor for number 16. What about 17? What type of inhibitor does the following graph best describe? Here's what I want you to do. I want you to pause the video right now, and I want you to try to do this one on your own. Okay, you didn't pause the video. Nice, I like you. You're a rebel. So the first thing you got to do is you got to go to your -1/Km, which is this one over here. What can you tell me about the Km? Has it increased or has it decreased? Because the x-intercept is shifting to the right, which means that it's getting smaller, that means that the Km has actually increased. because if Km increases, then negative 1 over Km decreases. So Km has increased. And look at the y-intercept, which is 1 over Vmax. Vmax has stayed the same. So what type of inhibitor is this? Perfect. Great job, as always. This is a competitive inhibitor. All right, so get comfortable with each of these Lineweaver-Burk plots and be able to recall what type of inhibitors belong to what graph. Excuse me. I just had a soft beverage. Okay, number 18. Which of the following is true of competitive inhibitors? A, binding to the ES complex is facilitated through an open allosteric site. Do competitive inhibitors bind to an open allosteric site? No, they do not. Where do they bind? Where do competitive inhibitors bind? Yes, they bind at the active site, not an allosteric site. So A is wrong. What about B? The inhibitor resembles the substrate, at least in some respect. That is true. What about C? The apparent Km is lower in the presence of the inhibitor. The apparent Km is the Km of the enzyme in the presence of an inhibitor. So does a competitive inhibitor change the Km? Does it increase it? Does it decrease it? Or does it keep it the same? With a competitive inhibitor, Km increases. And what this says is that the apparent Km is lower. Is that true or false? That is false. So C is wrong. What about D? Competitive inhibitors can be outcompeted with saturating substrate conditions. The answer is yes. I mean, the answer is it's F, but it's also a yes to D. Okay, some of you might be wondering, what are saturating substrate conditions? All this means is that if you have an enzyme and here you have a substrate and here you have the inhibitor and they're both competing for the same active site, you can outcompete the inhibitor with saturating substrate conditions. So you can just increase the amount of substrate, and by increasing the amount of substrate, you increase the likelihood that the substrate will bind and not the inhibitor, which will allow for the formation of the ES complex, which will allow for the formation of product. And so this is why Vmax stays the same. We can outcompete that inhibitor. All right, so the answer for number 18 is F. And number 19, reversible inhibitors of enzyme catalyzed reactions can be characterized by examining double reciprocal plots of reaction kinetics, aka Lineweaver-Burk plots. Essentially, all that means is that we can actually tell what type of inhibitor we have based on these Lineweaver-Burk plots. In the case of non-competitive inhibitors, in the case of mixed non-competitive inhibition, the presence of the inhibitor yields a curve that A, crosses the 1 over V axis at the same intercept as in the absence of the inhibitor. That is false. If we look at our mixed inhibitors, they do not cross at the same y-intercept as in the absence of the inhibitor. Here, you can see that it's clearly gone up. So they do not cross at the same point. So A is wrong. What about B? Crosses the 1 over substrate axis at the same intercept as in the as in the absence of the inhibitor. That is false. Look at this. Either it shifts it to the right or it shifts it to the left. So the 1 over S intercept, right, that's the x-axis. the 1 over S intercept is different for both of the non-competitive mixed inhibitors, which means that B is also wrong, because B, it says that it crosses the 1 over S axis at the same. It doesn't. It crosses it at different points. So both A and B are wrong. What about C? Crosses the 1 over S axis at a point different than that in the absence of the inhibitor. Is that true or false? That is true. Look at that. So here it crosses it to the left of the original 1 over S axis, and here it crosses it to the right of the original 1 over S. So therefore C is true. What about D? The presence of the inhibitor yields a curve that is parallel to the curve determined in the absence of the inhibitor. Does it yield a curve that is parallel to the curve determined in the absence of the inhibitor? No. So here the two slopes are not equal. So this is slope 1 and this is slope 2. They're not really equal, so therefore that's not true for that one. And the slopes for these two, so we'll call this M1 and this one is M2, they are not equal either. Different slopes. So these lines are not parallel. That's what that means. Obviously this one's not parallel to this one, but this one kind of looks like it, although it shouldn't be. Here, I'm going to redraw that. This isn't good enough for you guys. You deserve better. So it'll look something like this. Okay? Look, I'm trying my best, okay? Alright, that's all I got. So that's the whole weekly review. Congratulations for making it this far. I know this was a bit of a long one, but you guys deserve the best. So yeah, thanks for watching, and if you like the video, please go ahead and give it a thumbs up. That lets my bosses know that I'm doing an okay job. So yeah, thanks, and good luck on your exam, and good luck in the rest of the course. And I'll see you next time.